This is Calculus 6-1, Day 2, working with slope fields and differential equations. Well, we've worked with some diffie-qs some this year, but one thing that's very common in the AP test is that you have to draw yourself a slope field. So, I thought I'd do a demonstration. When you're asked to draw a slope field, you have to remember that they're usually going to indicate what points you have to draw. This one, the scale's kind of bad, but if you are taking notes on this one, it has a scale of 1. Here's 1, 2, and 3. Alright, so we're supposed to draw a slope field for this. Now remember, all a slope field is a graph of unit vectors, and they don't necessarily have to be a full unit long, but it's going to be a graph of segments that indicate the slope. So the way you're going to approach these is you're just going to, I don't know, I like to use a table of values. I'll just indicate my points that I'm going to use and consider what the slope would be at each of these points. Once you know that, all you do is draw a quick line segment at approximately that slope. Now when the AP graders reach one of these and they're grading you, which we have seen this on about every third test, okay? So if I had to predict, I would say you guys are due to see one just like this on the College Board exam coming up. So let's take a look. If I look at this, usually it's good to try to find some sort of pattern. Analyze numerically what's going on. It's just 2 times the y value, so the x value is not really going to matter. As I go left and right, I would expect them all to be parallel. And this is super common because we can't expect you, what is there here? I don't know. 3, 6, 9, I don't know. There's got to be like 36 points here for us to graph a line segment through. So what they generally do is give you something where there's a pattern to be realized. So if you look at this, you realize the x value does not matter. And what we're going to essentially do is take the y value times 2, and that will indicate the slope. So if I'm, for example, starting at -2, all you're going to see here is that the slope is twice that value. So very obviously, okay, now the question is how accurate do I have to be? How nice do these graphs have to be? Well, you can see that it's scaled out for me by 1 by 1 at the y values of -2. So basically, all the way along where y is -2, I'm going to make sure that dy dx is -4. So if this is -1 slope, so sometimes I'll do this when I'm trying to graph these and be really careful. If this is -1 slope, falling for a slope of -4 would mean down 1, 2, 3, 4, and over 1. So if I'm parallel to something like through there, that would be a slope of -4. So I'll just kind of lightly envision that if they give us one of these dot matrices and then try to draw the necessary slope segments. Okay, so when y is -2, I'm going to try to stay parallel with this. So here's where y is -2, and I'm going to just stay really steep. The length of these, they need to be long enough to indicate the slope, but don't worry about them too much, and you can tell I would say that would be suitable. I don't necessarily have to get out like a ruler and measure it both directions. So when y is -1, I need the slope to be -2. So I might come up here and go down 2 and over 1. I need to make sure it's parallel to that. Alright, so something like this. Oops, that wasn't all that good. See, there, I did a nice example of what not to do. Okay, so about like this. Nice. So you realize the pattern, you draw them across, nice line segments, concentrating on staying very parallel with these. Okay, now very frequently, and it's good to recognize this both directions, very frequently we are going to run into an area on the graph where the slope is 0. Notice here that anywhere y is 0, the slope is 0. So that's nice. That won't take but a second to do. Draw a bunch of horizontal line segments across right there. When I find x equals doesn't matter and y equals 1, I need a slope of 2. So across here where y is 1, I'll have a slope of 2. That's the same as rise 2, run 1. So I try to stay parallel with something about like that. And lastly, when y is 2, x is 4, and I'm going to keep a very steep slope. See, I am envisioning it, and I'm going to draw this in for you so you see the way I'm thinking. What I do is I try to think again, all right, what would a slope of 4 look like? It would be up 1, 2, 3, 4 over 1. That's pretty steep. So as I go across here, I'm trying really hard, being very careful, to be parallel with that. And that is what a successful slope field looks like. Okay, now the directions are going to shift on us, and they will ask us once in a while to find and sketch the solution. This time I'm asked to find a particular solution that goes through this point, 0, 4. So I don't know how well this is coming through for you. The graph's a little rough, but there's 0, 4. I have to sketch the solution that goes through the given point and sketch a slope field for this differential equation. So again, I might do a 2-column deal, and I'll get you through this one real quickly here. Go x, y, and if dy dx, that means the slope is going to be y plus xy, right? Okay. So I might just pick a few points to try to get the gist of what's going on. So 0, 4. This time the x value matters. 0, 3. So very often what I'll do, though, is try to realize a pattern and then just utilize that to continue. So let's take a look. If x is 0, y is 4, oh, this is nice. This will always cancel out. So this will just be the y value over here. M will be 4. This is canceling. M will be 3. M will be 2, and so on and so forth. That's if x is 0. So that means along the y-axis, whatever the y value is, that's what the slope will be. So I might come along here, and let's see if I can do this nicely. Steep at a slope of 4, then at a slope of 3, now at a slope of 2, now at a slope of 1. Oh, that's hard. Now at a slope of 0, and -1, and -2. And so on and so forth. So, generally I'd use a ruler and I wouldn't quite make an S here, but it's pretty tough with a stylus. But you get the hint. Like, the idea here is to find this pattern so that you're not literally calculating every single one of them. Let's try when x is -1. If x is -1, and I just spiel through a bunch of these, what kind of pattern do I realize? Let's see, it'd be 4 plus a -1 times the y value. Well, that's kind of nice. That'll be -4. Wait, now that's going to happen for every single one of these, that I'm going to get a slope of 0 when x is -1 and y is 4. All right, what about -1, 3? Notice the same thing will happen. So sweet. That means everywhere where x is -1, I'm going to end up with a slope of 0. Well, that makes that go really quickly, doesn't it? So this is the kind of thing I want you to see, is how to generate this slope field really quickly. And notice if x is 1, and let's start with 4 for the y value, I would get 4 plus 4, really steep, 8. Anywhere x is 1, we're essentially going to end up, if you look at just look at the numerical way of this equation, and you see that we get 3 plus 3. So you're basically doubling the y value to get your slope. Okay, but these are really steep. Don't be too concerned about it. Just try to make them show what you intend to show. Like a slope of 8 is incredibly steep and really, really difficult to show. Even a slope of 4 here. Let's see, what would that be? 1, 2, 3, 4 over 1. So that's still really steep. I'm having a hard time with the stylus. But gradually they come down. 1 plus 1 would be 2, so I'd have a slope about like this. What about when x is, now I might take a break here, go over and consider 1, 0. What's up with that? 0 plus 0. Okay, it still is working. M equals 0 here. And when x is 1 and y is -1, I'm back to -2 for the slope. So it just switched directions and is twice as steep as the y value. Okay, so that gives you a general idea. Now let's go through the second part of this question, which is finding the solution that passes through the given point. When you're solving a differential equation, This process is called separation of variables. You want to find a way to get the y values with the dy differential and the x value with the dx differential. Well, you might initially think, well, that's easy enough. I'll just do this thing here. We'll just go whop, 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 and we will move the dx on over there like so, right? Well, you're probably thinking like the normal way to solve this equation is to subtract y. We don't want that. We can't have dy like minus y. Like, we don't integrate that sort of expression. What we need is dy to be multiplied by some quantity which contains the y values. So what I mean to say is we want to factor y out of the expression. So dy equals y, and then I have a 1 plus x dx. You can see division will get it over there. This is going to be a pretty common kind of pattern. I got a 1 plus x dx. And now I'm ready to integrate both sides. 1 over y, that's natural log of absolute y. And then x plus 1/2 x squared plus c. Reminder, you can put the c on either side. I would like to keep it on one side and then stay consistent with this. Alright, now they have identified a point to find the solution that goes through it. So this is a particular solution passing through 0, 4. So if ln of 4 makes this equation true when x is 0, then we know c is natural log of 4. Alright, so finishing, I can say that natural log of y is x plus 1/2 x squared plus ln of 4. Well, I want y in terms of x, which would mean I shall e-base both sides of the equation, getting y equals e to the x plus 1/2 x squared plus natural log of 4. And that's about all I can do with that. Now that's a nasty looking equation, but drawing the equation through the solution point 0,4 indicates that when I come through here, I just want to make sure I end up very parallel. Now, maybe I should have went and found like at -2, 3 what that slope field point looks like. Okay, so I found that the slope there is approximately equal to -3, and that'll just help me so that when I go to draw my particular solution through our point 0, 4, I'll make sure that as I pass by these line segments, I make sure that I stay parallel to whatever I'm passing by. Okay, so very steep here at the beginning, and since I'm supposed to pass through 0,4, I'll start there. So it goes right off the graph, no worries. But as I come down in here, I can tell it has to level off and then get very steep again right away going off the other direction. This is the way this works. Many times you're only able to graph a part of the solution because the particular solution takes you right off the graph paper. Okay, so there's a couple of examples of working with slope fields, and we're going to work through a few exercises. Thank you.